So, in the last lecture, we learnt about Legendre transform. Legendre transforms is an important tool in physics. You already have used it. You have used it in thermodynamics, and now we are going to apply this in classical mechanics. Okay. So, let me first begin by describing the motion in Lagrangian formulation. See, we describe the motion in Lagrangian formulation by describing a trajectory in a configuration space. Configuration space is a n dimensional manifold if your system has n degrees of freedom. Now, what happens there is we describe a point q in the manifold. For that point there are n generalized coordinates, and then of course, as the system moves, this point will move in the configuration space and you get a trajectory. So, the aim of this exercise is to obtain the trajectory. Now, the trajectory is of course governed by the Lagrangian. Remember, all the forces are included in your Lagrangian, and the aim of the exercise is to determine the trajectory. And how is this trajectory determined? We know that from Newton's laws or in the Lagrangian formulation, the curve that obeys Lagrange's equation is the curve along which the system will move. Okay. And that equation is given by the Lagrange's equations or set of Lagrange's equations here. These are of course n second order differential equations in dependent variables q1 to qn, and of course independent variable t. Okay. Now, what we want to do is thus: this description happens in the configuration space. Now, in the last week we introduced the notion of phase space. Remember, the phase space is 2 n dimensional space, and the n coordinates are same as the n generalized coordinates, as the remaining n coordinates were the generalized momenta. Okay. So, the point there was described by q p. Remember, q here represents n generalized coordinates and p here describes n corresponding the generalized momenta. Okay. So, what is the motion described in phase space as? What is that equation which is satisfied? Because the aim here would be to find these functions q of t and p of t. This will describe the motion in phase space, and the equation of that curve is what we want to find. This is what is called as a Hamiltonian formulation. So, the Hamilton's equations determine the trajectory here. Okay. Let us start by first considering a very simple case. Take a system with 1 degree of freedom. Okay. So, here the Lagrangian of the system, the Lagrangian is given by, remember, there is only 1 degree of freedom in the system. That means there is only one generalized coordinates. I will just denote it by q, and q dot is its corresponding velocity. Okay. Now, the claim that we are going to make is I construct the Hamiltonian function by taking a Legendre transform of the Lagrangian. So, but when we are taking that Legendre transform, we do not want to take a Legendre transform with respect to all 3 variables, that is q, q dot and t, but I just want to take a Legendre transform with respect to one variable, that is q dot. Okay. Now, remember, generalized momentum p was defined as del L by del q dot. Okay. This perfectly fits with the idea of Legendre transform we had described earlier, but this p of course will be function now of q, q dot and t. Now, when will this be invertible function? Remember, the Lagrangian must be a convex function of q dot, then P will be monotonic and hence it will be invertible. So, if Lagrangian is convex function, then I should be able to write by inverting this function, I should be able to write q dot as a function of variables q, p and t. Okay. Once we do this, then of course, I can take a Legendre transform now. But is this a reasonable assumption that your Lagrangian is a convex function of q dot? Well, typically in most cases, the Lagrangian is simply quadratic function of q dots. Remember, how does this come from? Your kinetic energy term is of course quadratic in the x dot square, y dot square and so on, and when you make a transformation to generalized coordinates, all that you get is possibly a quadratic function or a polynomial of degree 2 in q dot. And when that happens, we know how to take a inverse of that function. Okay? Fine. So, once we have defined this, I will define now the Legendre transform of Lagrangian as Hamiltonian, denoted by the letter H, and call it as Hamiltonian. Remember, the function Hamiltonian is function of q, p and t. Okay? All right. Now, the question we want to ask is this: how do I get the equations of motion? Okay. So, let us first write down the H. H then becomes, so let me be a little more careful and write all the variables. Remember, in classical mechanics, it would be useful for you people to always keep track of functions and its arguments. Given function, it is a function of which arguments is a question you should be asking yourself all the time. So, H is a function of q, p and t, and we will define this, of course, Legendre transforms are defined this way as p q dot minus L. Again, if I want to be careful, I will write it like this: P, then q dot, remember, is function of q, p and t minus L. L in turn is function of q, q dot, but q dot is function of q, p and t and t. Okay. So, this is the complete description of H. Remember, when we construct H, I will have L, which I know in terms of q, q dot and t. Look at the q dot, substitute q dot from here, okay, so that it becomes a function of q, p, t, and then put it back into the entire equation to get an expression which is function of q, p and t alone. Okay. Now, this is the way you have constructed the Hamiltonian. Now, I want to find out the equations of motion. Okay. So, here I have already written the Hamiltonian. Let me start by taking a partial derivative of Hamiltonian with respect to q. So, when I take a partial derivative of H with respect to q, on this side, remember, when we are doing this, q, p and t are the independent variables. So, on this side, p of course is independent variable, and it will simply be derivative or partial derivative of q dot with respect to q minus the Lagrangian here del L by del q, but Lagrangian is also function of q, an implicit function of q through q dot. So, I will also do this, take a partial derivative of L with respect to q dot and del q dot by del q. Now, notice what is del L by del q dot? Oh, this is nothing but p. If this is p, look at the first term and the third term, they cancel each other, leaving you with just del L by del q. Okay. Remember this, that this particular case, the partial derivative of L and partial derivative of H, these are two different things. They mean different things on either side. When you are taking partial derivative of L with respect to q, you are holding q dot and t fixed, whereas on the left hand side, when you are taking partial derivative of H with respect to q, you are holding p and t constant. Okay. So, they mean different things. Now, I will employ here the Lagrange's equations, in which case this is nothing but minus d by dt of partial derivative of L with respect to q dot, but this is nothing but minus d by dt of p, which I will denote as p dot. Okay. This is one equation. Now, let me also calculate partial derivative of H with respect to p. Now, of course, the p q dot is a product of two functions. So, I will write this as q dot, then plus p times del q dot over del p and minus derivative of Lagrangian, but Lagrangian depends on p only through q dot. So, that will be del L over del q dot into del q dot by del p. And again, just like the first equation, you notice that this here is nothing but p, and the second term and the third term, they are identical. So, this gives you q dot. Okay. These two equations here, 1 and 2, these two equations are actually the Hamilton's equation, which I have put them in this form here. I will also go ahead and calculate the partial derivative of H with respect to t. Okay. When you calculate partial derivative of H with respect to t, remember this will be p, then del q dot by del t, and minus there is a del L by del t. That is because L is a explicit function of t, minus L also depends on t through q dot. So, it is del L by del q dot into del q dot by del t, and again you can immediately notice that this is equal to del t. Okay. Fine. So, we have now equations of motion which are called as Hamilton's equation. So, I will collect these equation number 1 and 2 and put them here in this form. I will put q dot on the left hand side, p dot on the left hand side, so that they look like differential equations in p and q. Okay. So, one equation is this and the other equation is this. These are called as Hamilton's equations. Okay. Fine. Now, look at the symmetry of this. It is a nice thing that happens, that now momenta and coordinates or p and q, they are almost on the same footing, and there is a the structure of the equations has a nice symmetry, and because of this symmetry and simplicity, these equations are also called as canonical equations. Out of this, q of course will become canonical coordinate, p would become canonical momentum, and also the pair together q and p are called as together as canonical variables. Okay. Fine. Now, one more comment that I would like to make. Remember this Hamiltonian, when we took the Legendre transform, the Hamiltonian here, which is PQ dot minus L, does not it look exactly like the energy function which I had discussed about in our second week. So, the energy function typically we denoted it as H was also written as del L by del Q dot minus L, and out of which if you immediately recognize the partial of L with respect to Q dot is nothing but P, which is momentum, then these two functions look identical. But wait, they are not identical. That is because they are defined on completely different spaces. H is function of Q, Q dot and T, and so that is why it is called energy function, and capital H is a Hamiltonian which is function of Q, P and T. We make this distinction very clear that these two functions are not same, at least mathematically definitely not same. But it may happen that in a given system, this energy function may actually represent total energy, and in that case the Hamiltonian also will represent the total energy. Okay. Now, let me extend this formalism to several variables. So, you start with n degrees of freedom. My generalized coordinates are q1 to qn, and together I denote those by letter q. And then you have Lagrangian, which is function of qn corresponding qn dot and t. And now we want to take a Legendre transform, but not with respect to just one q dot, but all n q dots. So, define Pj, that is a canonical momentum, as derivative of L or partial derivative of L with respect to Qj dot, and then the Legendre transform of L, which is Hamiltonian function, now can be written as sum over Pi Qi dot minus L. Same comment? Okay. Now when will these, so basically you have Pj's which will come out as a function of, so these will be functions of Q, Q dot and T, and remember in that Q dot you have Q1 dot to Qn dot. We want to invert this. So, what we want is Qj in terms of Q, P and T. Remember again here the P here represents n variables, which is P1 to Pn. When will this happen? That is when the Lagrangian is a convex function of q dots. Okay. So, what is the condition? Remember we had written there that the determinant of the Hessian, and how would I define the Hessian? It is the matrix formed by del Qi del partial Qj. Of this Hessian matrix, determinant should be greater than or equal to 0 if there are two variables, and to be very clear or accurate, what must happen? The eigenvalues of the Hessian matrix must be all positive, and we will make that as a reasonable assumption in this case. Again, if Lagrangian is quadratic function of q dots, our purpose is served. Okay. Fine. And in this case, I will ask you people to derive these equations and show that we get 2n first order differential equations, which is Qi dot, remember these are also functions, say this equation actually is a restatement of the q dot functions here. So, q dot here will be equal to partial derivative of h with respect to Pi, and Pi dot will be equal to minus of partial derivative of H with respect to Qi, all way 1 to n. So, there are 2n differential equations which are first order differential equations. What do? They actually are replacing n second order differential equations. Okay. However, there are advantages in doing Hamiltonian mechanics here. We can plot the trajectories in phase space, we can look at the phase space portraits there. So, there is of course merit in solving this. It actually may happen that by writing these as 2n first order differential equation, we might think that we are trying to make things simpler from the calculation or computation point of view. Actually, in most cases that will not turn out to be the case. Eventually, when you have 2n differential equations which are first ordered, it is very likely that we would probably change them to n second order differential equations and probably solve the problem. But that is not the point here. Okay. Now, let me compare the Lagrangian formulation with the Hamiltonian formulation. Now, here I have already written down the entire summary. So, in the Lagrangian formulation, we use configuration space, which is an n dimensional manifold, whereas in the Hamiltonian the description is in the phase space, that is 2n dimensional manifold. Now, variables there in the Lagrangian formulation are the generalized coordinates, but in phase space we now describe the state of the system using q variables and p variables. So, it is a point in phase space with 2n coordinates, out of which n are same as generalized coordinates of the configuration space. The remaining n coordinates would be your generalized momenta or conjugate moment. And the motion here is described by a trajectory similar to a trajectory which is given in phase space, but now we have advantages of phase space. You see, trajectory uniquely describes a motion, whereas in case of Lagrangian formulation or in configuration space, two different motions could have same curve in the configuration space. Remember, the trajectory also means the dependence on time t, and when I just say curve in configuration space, I am saying giving an equation of curve in terms of the coordinates alone. Okay. The dynamical function which determines or governs the motion and gives you the trajectory is Lagrangian, and in this case it is a Hamiltonian. Finally, the equations of motion, there are there are n second order differential equations, second ordered, and in this case we have, so in this case we have 2n first ordered differential equations. Okay. And for the completeness sake, I have also written the time derivative of the Lagrangian and the Hamiltonian. And if you notice here that the Lagrangian, if it is independent of time, okay, then what remains conserved is not the Lagrangian itself, but it is p q dot minus L, which is the energy function. Whereas, good thing about Hamiltonian formulation is if the Hamiltonian is independent of time, that is it does not explicitly depend on time, then the Hamiltonian itself is the conserved quantity. Okay. Now, I will take few simple examples. Let me just take one particle with 1 degree of freedom, okay, and the Lagrangian is given by, remember in this case there is only one variable. So, it is half m q dot square minus some u of q. Now, the generalized momentum here will be q dot, which is nothing but m q dot. And now you can immediately see this is a neatly invertible function, and q dot is nothing but p by m. Let us calculate the Hamiltonian. So, the Hamiltonian H will be equal to p q dot minus L, and let us substitute various quantities there. This is p, there is a q dot which is p by m minus the Lagrangian is half m. I will substitute q dot. So, that is p by m whole square plus u of q, and it simplifies very easily to p square by 2m plus v of q. In this case, of course, this will also represent the total energy of the system. Now, one more example. Suppose I have a Lagrangian which is given by, so Lagrangian is function of r dot theta, theta dot and t, and this is a again for a single particle moving in a plane using polar coordinates. So, this would be half m r dot square plus r square theta dot square minus u of r comma theta. So, this is your Lagrangian. Calculate PR. PR will be equal to m r dot, and p theta will be equal to m r square theta dot, and both these are invertible very easily. So, r dot, this implies r dot is equal to p r by m, and theta dot is equal to p theta by m r square. And you can of course identify this. This is nothing but angular momentum divided by moment of inertia. Okay. So, write down the Hamiltonian. So, Hamiltonian will be equal to, remember it is a summation over all generalized coordinates, which means I will write this in explicit form. It is PR r dot plus p theta theta dot and minus the Lagrangian. Okay. So, this will be equal to PR, r dot is nothing but, so I will write this as PR square by m plus, then this will be p theta square by m r square minus the Lagrangian. Now, this is half m, r dot is nothing but p r square divided by m square plus then r square theta dot. So, that would be p theta square divided by m square r to the power 4 and plus u of r comma theta, and this simplifies to p r square by 2m plus p theta square by 2m r square and plus u of r comma theta. Okay. So, this is how we construct the, and then I will also write equations of motions in this case. Equations of motions, remember there will be 4 of them. So, here r dot will be equal to partial derivative of h with respect to p r, and now we have Hamiltonian here. partial derivative of this is nothing but PR by M. Remember, this would anyway will give you the same equation that you got by inverting the relationship between conjugate momenta and the generalized velocities. And also theta dot will be equal to partial derivative of h with respect to p theta. P theta appears here. So, this is nothing but p theta divided by mr square, and PR dot will be equal to partial of h with respect to r. This will be equal to, so here notice that there is a r appearing here. So, I will write this as p theta square by 2m into minus 2 by r cube plus, so sorry, I forgot the minus sign, so I will put that minus sign there, plus so there is a minus sign from outside, and that would be del u by del r, and this of course will become PR dot minus p theta square over mr cube, and you can see that this is the familiar form of the equation in terms of PR and p theta. And similarly, we can obtain the final equation, which is, so this is equation number 1, 2, 3, and the final equation, which is p theta dot will be equal to the minus by del theta, and in this case of course theta only appears in u. So, that will be equal to minus del u by del theta. Okay. And if you want, we can sort of think of this as r times minus del u by r times partial theta. If you recognize this, this is nothing but the tangential force in the direction of theta cap multiplied by r, that gives you the torque above the origin. And what do you have here? P theta. If you look at what p theta is, oh, what is that? That is angular momentum. It is the dl by dt is equal to torque equation. Okay, that is what we expected to get anyway. Okay. One more example. Now, if you have a charged particle moving in a constant or uniform magnetic field. Okay. Let me choose B, which is in the direction of z cap. So, this is B vector is in the direction. The Lagrangian for this is written by the charged particle, of course, has a charge of E. The Lagrangian is given by half x dot square plus y dot square plus z dot square minus, if you remember, the Lagrangian for charged particle in electromagnetic fields, we had this q phi minus q phi plus q v dot a, where a was the vector potential corresponding to the electromagnetic field. So, I am simplifying that finding a actually can be written as half of b cross r vector. After having done all that calculation, you get E b by 2c, and this will be x y dot minus y x dot. So, this Lagrangian, even if you forget how to calculate this, let us accept this as a Hamiltonian, this as a Lagrangian of the system. Now, what are the equations of motions? First of all, we are going to construct the Hamiltonian from this. So, P x will be equal to del L by del x dot, which will be equal to mx dot, but wait, the x dot is appearing there in the other term too. So, this will be equal to plus EB by 2c into y. Py similarly is del L by del x del y dot, which will be equal to my dot minus EB by 2c times x. Okay. So, we can of course calculate, and there is a Pz too. Pz is nothing but mz dot. We can invert all these relationships very easily. So, your x dot is nothing but 1 over m p minus EB by 2c times y, okay, and y dot is 1 over m py plus EB by 2c times x, and z dot is Pz by m. Okay. So, we have calculated all of this. Now, let us calculate the Hamiltonian. So, the Hamiltonian will be the trick that I am going to do is this. Remember, I have Px x dot plus Py y dot plus Pz z dot minus L. Okay. Now, I can substitute x dot by the corresponding expression which we have obtained here. Instead, what I am going to do is in fact substitute Px in terms of x dot. So, this will be equal to mx dot plus EB by 2c times y, that is your Px into x dot, plus Py is nothing but my dot minus EB by 2c times x into y dot, plus Pz is nothing but m z dot into another z dot. So, mz dot square and minus the original Lagrangian. Original Lagrangian is in terms of, remember, x dot, y dot and z dot. Okay. So, simplify this and you would get half m x dot square plus y dot square plus z dot square. There. This actually simplifies quickly, but I should not leave my answer in this form. What do? Of course, the Hamiltonian must be expressed in terms of generalized coordinates and momenta. Okay. So, but that part is very easy here, because then this would simply become in the bracket your Px minus EB by 2c times y whole square plus Py plus EB by 2c times x whole square plus Pz square. There. And then of course, you can expand this again, and that is how you would get the Hamiltonian, and then we can use the Hamilton's equation to calculate the remaining variable, the equations of motion. After having seen these examples, now we can actually do little formal work. In the sense, there is a large class of Lagrangians which fall into a neat form, and we may be able to write down a direct formula for Hamiltonian from the Lagrangian form itself. So, let me start by writing down the specific form. In this case, the Lagrangians, remember, if you are making transformation to generalized coordinates, then the kinetic energy in Lagrangian is a quadratic function of the Cartesian coordinates. Now, once you transform that to generalized coordinates, then In most cases, the Lagrangian will have a form where it will be quadratic in q dots if q is a generalized variable. So, I will write this form here. Lagrangian has a form which is, I will write L 0, which is function of q and t. Remember again here q represents the n generalized coordinates, plus a term L 1 which is function of q dot, but we will assume that this L 1 term is only linear in q dot, plus the second term, and we will assume again here that the L 2 term is only quadratic, quadratic in q dot. Okay. So, what can be the form of L 1? L 1 must be, let me write down the degrees of freedom is equal to n, which means you have generalized coordinates going from q 1 to q n. Okay. So, the form of L 1 now will be, it is linear in q dot. So, I will write it as sum over I, sum a I and q I dot. But remember, a I themselves are not really constants, they can be functions of q and t. So, a I are functions of q and t. In the same way, I will write the second term L 2. L 2 is, can be written as sum over I and j. Remember, both these variables I and j go from 1 to n each. So, there will of course be a double counting, but all that has been taken care of in the matrix T there, which I am in a moment going to write. So, I will write this as T I j, and remember these T I j's are in turn functions of q and t. Fine. Now, from here I want to calculate the Hamiltonian. So, what I am going to do is put this in a neat matrix form. So, let us start by doing this. I will write Q as a matrix with n rows. It is a column matrix with n rows. So, you have Q 1 and all the way entries up to Q n, and to distinguish this from usual notation, I will put one tilde here. That means it is a matrix. So, your Q dot matrix will also look like Q 1 dot to Q n dot. Okay. All right. So, this is your Q dot matrix. In addition, now I need A 1 or these coefficients A I of Q I dots. So, I will put that also in the matrix form. So, your A tilde is a column matrix with entries A 1 to A n. And finally, that leaves us with T I j. It is a square matrix, n by n matrix. Okay. So, I will write this as T tilde, I will write this as T tilde, and the entries that go in this matrix are T 1 1 goes up to T 1 n, and down the column that is T n 1, and finally, on this side you have entry T n n. Okay. Now, I have put this in a neat matrix form. I will write down the term L 1 in terms of matrix now. So, your L 1 will look like A tilde, and if you take a transpose and then Q dot tilde. Okay. Can you see that this transpose of A multiplied by Q, this is now after taking transpose, this is 1 by n matrix and this is n by 1 matrix. So, your result is again L 1, which is a scalar number, which is what we expected here. So, this is exactly what we would get if you put it in the matrix form. Now, how would the L 2 look like? So, L 2 would look like half Q dot tilde transposed T matrix and Q dot. Okay. One quick look at this structure of L2, you see the pairs like Q1, Q2 will appear twice, also it will appear as Q2, Q1. So, clearly this matrix must be symmetric, which means transpose of this must also be the same matrix. Okay. Okay. Now, we are in position to calculate the Hamiltonian. The first thing that I will do is calculate generalized momenta. So, put generalized momenta also in the matrix form. So, you have entries like P1 to Pn, and this is nothing but I am going to write this as symbolically del L by del P. We could write it as gradient of L with respect to P, gradient with respect to Q dot with respect to Q dot. Okay. Now, what will this come to? When you take a derivative of L1, all that you will get, if you are taking derivative with respect to Qj dot, all that you are left with is Aj. And for the L2 term here, for this L2 term here, when you take a derivative, then all that you will be left with is summation over I Tij Qj. This is when you take a partial derivative of L2 with respect to Qi dot. Okay. So, let me write the final result here. What would this come to? This would be A tilde, that is the A matrix, plus T times Q dot tilde. Okay. Do this term by term, write down the individual term. For example, Pj will be equal to del L by del Qj dot. Okay. Derivative of L0 0, derivative of L1 will give you Aj, plus when you take a derivative of L2, what do you get? That would be summation over I Tji Qj dot. Okay, fine. So, this now can be neatly put in the matrix form which I have written here. And remember, the Lagrangian here is quadratic, it is convex function, and hence Q dot can be easily found by inverting this relationship. So, when I invert this relationship, I get Q dot tilde. So, after inverting, this would be equal to T tilde inverse into P matrix, I will put the tilde here too, minus A tilde. Okay. This is what you get after inverting this relationship. Now, let us put all this back into the Hamiltonian, in the definition of the Hamiltonian. So, Hamiltonian, this is nothing but there was a summation over Pi Qi dot, okay, which I am simply going to write it as. So, you have P tilde transpose Q dot tilde minus the Lagrangian, and let us write down individual terms there. So, this is P tilde transpose into Q dot tilde minus L0 minus L1 was nothing but A tilde transpose into, let me first write the whole expression and then I will make a substitution, minus half, this was Q dot tilde transpose T matrix into q dot matrix. Okay. Now, substitute q dot again, q dot tilde was nothing but T inverse into P tilde minus A tilde. Let us substitute this back into this equation, and the Hamiltonian then will become P tilde transpose T inverse, and you have P tilde minus A tilde minus L 0 minus you have A tilde, and then substitute for q dot there. Substitution for q dot, you will get T inverse P tilde minus A tilde and minus half you have. So, we are taking transpose here. So, it will be P tilde minus A tilde transpose of this matrix, then T inverse, and remember it is transposed, but T was a symmetric matrix. So, its inverse is also a symmetric matrix, and hence I can simply ignore that transpose there, and then you have T tilde and T tilde inverse P tilde minus A tilde. Okay. Now, what happens to this? This of course, when you take this product, you will get identity times T tilde inverse will be T tilde inverse. And on this side, see here this term is common between these two, and you remember matrix product is linear. So, this will be P tilde minus A tilde transpose, then there is a T inverse minus A tilde, and then minus L 0 and minus half of, again it is the same term, P tilde minus A tilde transpose T inverse and P tilde minus A tilde, and this finally simplifies to. So, this is half of P tilde minus A tilde transpose T inverse minus L 0. Okay, there. So, we have straight away got the final answer out of this. And whenever we recognize the Lagrangian has this form here, quadratic form, then we can directly apply this formula there. Okay, fine. So, let me take one example. In the example, I will consider a charged particle let us say the charge is q. Okay. Take a charged particle in electromagnetic field, in EM field. In the EM field, now we remember how do we describe EM fields? That was using the scalar and vector potential. So, you have a pair of scalar potential and a vector potential, and remember our calculation in generalized potentials. This was the example, and what is the generalized potential in this case? Generalized potential U is given by q phi minus q by c times a dot v. Okay. That v there was the velocity. Okay. Now, let me write down the Lagrangian for this particle. Lagrangian L will be equal to, the kinetic energy is nothing but half m, and you have x dot square, y dot square plus z dot square and minus this potential. So, that is minus q phi and plus q by c a dot v. I will write this a dot v also in the expanded form. So, that will then become a x x dot plus a y y dot and plus A z z dot. And now notice there is a quadratic part. So, this is your L 2, this is your L 0, and the terms which are linear in q dot, or in this case x dot y dot z dot, this is your L 1. Okay. And recognize various pieces there. So, A tilde matrix is the coefficient of x dot, y dot and z dot. So, this is nothing but, so there is a q by c outside, and I will write this as A x, A y and A z. Okay. This is your A tilde. And what is your T matrix? T matrix is M times 1 0 0 0 1 0 0 0 1. Oh, but that is just M times identity matrix. Okay. This is 3 by 3 identity matrix. That makes it very simple, because then I can immediately calculate T tilde inverse. Inverse is simply 1 over M times the identity matrix there. Okay. And now let us write down the final form for the Hamiltonian. So, then the Hamiltonian has a form H which is equal to, so remember it was half, then you have P tilde minus A tilde into T inverse and of course transpose here, and there is a P tilde minus A tilde minus L 0. So, put everything together, the way Hamiltonian looks like is completely different. So, here now it will be half. From T inverse I will get that 1 over M. So, I will write it as 1 over 2 M, and what is there in P tilde minus A tilde? That is nothing but the first row of P tilde is P x minus the first row in A tilde is nothing but q by c times A x whole square, plus similarly you have P y minus q by c A y square, and similarly for P z z square, that is it, and minus L 0, but L 0 itself was minus q phi, which means this will become plus q phi. Then we can immediately apply the technique to construct the Hamiltonian out of this, okay, for the electromagnetic field. And remember, this Hamiltonian applies to any electromagnetic field that is calculated out of some scalar potential and the vector potential. Okay. So, in the next section I will talk about the cyclic coordinates and the conservation principles. Remember, while describing Lagrangian or during Lagrangian formulation, we had discussed these theorems, and for the Hamiltonian system, there are little bit of advantages there. So, I will discuss that in this section.